Yes, I cannot, so this lecture will not be able to compete with the wonderful boat trip from yesterday. I'll do my best. So what I did at the end of my talk yesterday was to introduce this category of motivic spectra over some base scheme S, and to give some examples like shifted suspension spectrum. So M being some natural number. So this is the spectrum starting with a couple of points and then in M. You start with A and then you suspend. And the structure maps are the obvious maps. So this here is a pointed space over S, and for example you can take a smooth scheme over S equipped with a disjoint base point. Yeah, these are sort of very basic. And I gave another example, the algebraic K-theory spectrum, which looks very periodic, so it's always this Quillen pre-sheaf of K-theory spaces, and the structure map is the weak equivalence of spaces over S, given by Quillen's computation of the K-theory of the projective line. And I'll give two more examples. I will follow closely Wołodzki's beautiful ICM lecture from Berlin, the only ICM I ever attended, but the next one is going to be here in St. Petersburg. So this is on top of our lists, our list of events to attend, I think. Yeah. So that would be in 2022. Yeah. I'll see you all there. Okay, so Wołodzki's ICM talk, he introduces two other theories. So one of them, yeah, since this is a bit quicker, is algebraic cobordism. It connects well with the topic of Nikita's lectures because it gives you the universal-oriented theory in the stable homotopy category associated here in a suitable sense. So what are the spaces? Spaces are atom spaces of tautological bundles over suitable Grassmannians. So the rth Grassmannian is the colimit in the category of pointed spaces over S, where you take the Grassmannian of rank R linear subspaces in an affine space of dimension D over S. Okay, and again, I should not forget to mention the structure maps, although, yeah, but I cannot resist. So the structure maps are given as follows. We have to give a map from the 2-1 suspension of the tomb space in the nth stage. That's this here, and we can identify this 2-1 sphere with the tomb space of the trivial bundle. So if we smash this with this tomb space, we can express this with tomb space of the direct sum. And this here, as it turns out, is the pullback of the next tautological bundle. where I is the sort of inclusion you get from adding a trivial line model. Okay. So from this here, you then get a natural map to the Thom space of the next stage. I shouldn't. Yeah. Sorry. Maybe like this. And this defines the structure map.
I upper star is a bundle over the Grassmannian M. Okay?
Yes, yes. So for I, you use the sort of the obvious colimit of closed embeddings of the Grassmannian of n planes and the Grassmannian of n plus 1 planes. Okay. Yeah, and the last one, although it was mentioned already, is motivic homology. Ah, right. Okay. So this here, it should get an index saying that it's over the base scheme S, and formally I introduced this only for S regular. This here works over any base scheme. There's also a version here over any base scheme. Don't worry too much. Motivic homology, as Wołodzki defines it, is also available in certain generality, but for certain statements it is best to assume that it's constructed over a field. So let me just quickly sketch one construction, which will probably not make it very clear how it is connected to the motivic homology that Matthias introduced. So the rough construction is as follows. You have smooth varieties over F, and you enlarge this to the category of smooth correspondences over F. So this functor gamma is the identity on objects, and the morphisms here from X to Y, this is a free abelian group on closed irreducible subsets of the product, and when you project down to the first component, you want this to be finite and you want this to be surjective on a connected component. Yeah, and there's a composition here. It's similar to what Nikita introduced in his talks when it comes to the category of Chow motives. So, if we have a pointed space now, so a presheaf here. I forgot. So this functor gamma sends a morphism to its graph. Okay, if we have a space here, we can make it abelian. So there's a free functor into the category of simplicial abelian groups, which sort of factors out the base point. And then you can left Kahn extend along this functor and get something here. Yeah, so if this here is A, this is the free presheaf with transfers generated by A. And of course here you can forget the additive structure and you can precompose with this functor here, which gives you a right adjoint to this functor here. And this allows us to define the spectrum as follows. So the nth space is, you forget the transfers, but you add them first to the 2n n sphere. And in order to define the structure map, it suffices to say that this functor here is a strong symmetric monoidal. So this here is a lax monoidal functor, lax symmetric monoidal, and you have the unit of the adjunction. Yeah, so you get a structure map, a map as follows. You have this here, for get transfers, after adding transfers to the 2n n sphere. You use the unit here. And then you smash. And then you use that these functors are lax monoidal, and then you multiply these two spheres together to n plus 2, n plus 1 sphere. And this gives you the structure maps. Okay. So, let me quickly define the stable homotopy category here. And again, I'm going to be not too precise. So stable equivalences. So this is the definition. If you want to call it a definition, stable equivalences in this category of motivic spectra over S. They are generated in a certain sense by maps of motivic spectra which are eventually level-wise weak equivalences of pointed spaces. Yeah, so there exists a natural number such that beyond this natural number every map of spaces, so maps in every level are weak equivalences. So here's the most prominent example of such a map. You take
in mind level.
Yes, level-wise motivic equivalences. Nice. So you take a shifted suspension spectrum and you start with something which is suspended already, and then there's an obvious map which is the identity in almost all levels to the mth shifted suspension spectrum of this. These are sort of the basic examples, and I can also give you a more precise definition regarding this generation. Say that a motivic spectrum E over S is stably fibrant if it satisfies the following conditions. So first of all, for every natural number En, this is a pointed space over S, and this is supposed to be fibrant as a space. So this can be phrased as follows. If I evaluate at X, this is a Kant complex. If I evaluate at the empty scheme, this is contractible. If I evaluate at the projection for the affine line, this is a weak equivalence of simplicial sets. What else do I have? Right. En sense Lisnevich distinguished squares to homotopy pullback squares. Yeah, this is saying that for every n, En is a fibrant space over S. And this you can sort of read off from this condition here. We want that En to 2 1 loops of En, that this here is a weak equivalence of spaces. And in this case, since these are fibrant, this is saying the same as this here. This is a weak equivalence of simplicial sets for every n and for every x. Now this defines this notion of being stably fibrant. And then
En plus 1?
En plus 1, yeah. So this is the adjoint to the n structure. Thank you. Thank you. Okay, and once you have this notion of being stably fibrant, you can say a map of motivic spectra. F is a weak equivalence if it induces a weak equivalence of simplicial sets of maps after inserting something stably fibrant here. Everything stably fibrant. You know, what you have to do implicitly here is to make sure that the domain and codomain of F are suitably cofibrant. You know, this clarifies what is meant by generated. Okay. By construction, this here is stably fibrant, and Blavatsky's cancellation theorem shows that this here is stably fibrant, and this here is not stably fibrant. Okay.
Can you say again what you said about F? So F is a weak equivalence if what is your condition?
Okay. Yeah, if this here is a weak equivalence in simplicial sets, then F, so this is a map of motivic spectra over S, is a stable equivalence. Okay. Further questions?
Could you just briefly explain why MJL is not stably fibrant?
So first of all, you have a problem with the single spaces here. For example, as it is defined, it is not clear why these spaces should be A1 invariant. Okay, for example, this space here happens to be equivalent to infinite projective space, which we know represents the PK group, so there is some A1 invariance, but I think already in the next stage there is an issue. You would have to apply the Suslin's singular complex to make sure that these objects become A1 invariant.
When you said this is weakly equivalent, that's something strange. I mean, this space should be without saying weakly equivalent to something, should be A1 invariant, and it is not. I mean, this is just an infinite projective space, and it is not A1 invariant.
Oh, yeah. So, yes, I should not have used the word A1 invariant, but instead, it is weakly equivalent to a space which is fibrant.
Every space is weakly equivalent to space.
Yes, it's a tautology, I'm sorry. Yeah. But yeah, P infinity itself, thank you for pointing this out, is not A1 invariant. There are many non-trivial maps from A1 to this space. I guess not to this one. Yeah. But from this one. Yeah, the other issue is that the adjoint of the structure map is not a weak equivalence. Yeah.
I would say that it has no chance to be a weak equivalence, because even in topology it is not the case.
Yeah. Yeah. Okay. Yeah, in some sense, this motivic spectrum is a bit too small. Yeah. Usually, fibrant things are very, very big. Okay. Right. So the stable homotopy category of S is then defined as the category you obtain by inverting these stable equivalences in the category of motivic spectra. And then we get a category in which the Hom groups I would like to abbreviate like this. And one can sort of, I mean, on my first lecture, I gave us a certain theorem describing some properties of this category. One thing I should mention in connection with Frédéric de Glis's lecture series, you have this adjunction, this base change adjunction if F is a morphism of base schemes, and this extends to this setup, and if F is smooth, you also have this F lower sharp extends, and the basic reason is that if you take the pullback of the 2-1 sphere, you get a 2-1 sphere. Now here I should say that this is over T and this is over S. Yeah, so it's a section of this fibered category. Again, if you want to apply these functors on the level of homotopy categories, you have to derive appropriately. Yeah, and there's also a monoidal structure. Which is denoted smash, and yeah, the better thing to define it is to use motivic symmetric spectra instead, but I can give you sort of a naive version. If you have two motivic spectra D and E, you can define the smash product as follows. In the even terms, you take the smash product of these pointed spaces, and for the odd terms, you take a suspension of these. And as a definition, this is, yeah, in some sense really quite ugly, because it is apparently not associative, and it has problems with being commutative as well, and even the unit property is not so clear. What is the unit? So this is the infinite suspension spectrum of the zero sphere. Yeah. But on the level of the homotopy category, everything works out. and you get a closed symmetric monoidal structure. And there is sort of one key property one can describe which allows this to go through, and the key property is that the cyclic permutation on 6-3. So if you take the threefold smash product of this sphere, this is homotopic to the identity. And I cannot resist sketching the argument why this is true. This is induced by up to A1 weak equivalence by a matrix operating on a quotient of affine 3 space. And this can be expressed as a product of elementary matrices, and every elementary matrix operates like the identity matrix up to A1 equivalence. So this cyclic permutation condition makes makes sure that this smash product works, and it also does the following. So from the definition of a motivic spectrum, there's an obvious equivalence on the homotopic category, which you get just by shifting the terms in the spectrum back and forth. What you actually want to invert is the suspension with the 2-1 sphere. And you can relate these two functors, and again, you can relate these nicely if you have this cyclic permutation condition. So what we also get basically from this definition and this key property is that this here defines an equivalence. And in particular, since the 2-1 sphere contains as a smash factor this 1-0 sphere, we get that it's triangulated. And because this triangulated structure, you get it by smashing with something, triangulated and monoidal structure are compatible in a suitable sense. Yeah.
Why do you consider this smash product but not a bouquet of, say, dk smash en minus?
Oh, like for tensor product of chain complexes.
Yeah. Why
Well,
does this work?
This is one option you have. Yeah, you have several
But
options.
Option also works as for chain complexes, for example.
Yeah, I mean this is in some sense you have many options, and this you can relate these sort of indexed over various subdiagrams of the lattice in the plane, and this will be what I have to say co-final choice in there.
The kind of bisequential set and take the instabilization to the diagram.
Yeah. I understand now. I really should have avoided giving this explicit definition.
Okay.
Yeah, it raises questions, which we can discuss, of course. But yeah, let's see. Let me erase this here. Is there some dry cloth as well? No, okay. Not really. Okay. these motivic spectra that I'm erasing, one can now ask what theories do they represent in this motivic stable homotopy category. And in the case of KGL, one gets algebraic K-theory over, so equivalent algebraic K-theory over a regular scheme, and well, there's a version over an arbitrary base scheme. This then represents homotopy algebraic K-theory. Yeah, the Allenbeck-MacLane spectrum represents motivic cohomology as defined, for example, using Bloch's higher Chow groups. At this point, yeah, I should probably add that there is a nice version also over Dedekind rings given by Markus Spitzweck. All right, and then in this connection, I should have mentioned that all these three motivic spectra that I erased have ring structures in this category. So with this definition, it's sort of, I mean, basically a ring structure amounts to a suitable pairing, and in all the three cases, it's fairly straightforward to write down a suitable pairing. And checking that this actually defines a ring structure, might be more or less work. But for MGL and for HZ, it's fairly simple. Let's see. There's regarding notation, I should introduce now the following. Since the 2-1 sphere is invertible, we have for every pair of integers a sphere in the stable homotopy category over S. And since this was explicitly mentioned in Frederick's talks, I would like to give you the following lemma. If you have a map of motivic spectra, it's an isomorphism in the motivic stable homotopy category. If and only if the following holds, the induced map on Hom abelian groups is an isomorphism. Yeah, of course, this is trivially true if you are allowed to enter all motivic spectra here, but it suffices to take these very special ones. So these generate in a suitable sense the stable homotopy category, and they form a conservative family. And I should also mention all of these are compact objects. So it's you get a compactly generated triangulated category. There's sort of one issue with sort of the duality. You would like all of these to be to have a strong dual, and well, there are some subtleties. Maybe I'll mention this later if you're interested. Okay, let me just sketch. Oh, yeah. Yes. This is an isomorphism. Sorry. Yeah. Okay. Let me quickly sketch the proof. So it, since we have a triangulated category, it suffices to detect whether an object is zero. Yeah. Check that E is contractible if and only if 0 for all SWX. And by construction, we can assume that E is stably fibrant. And so contractibility of this motivic spectrum is then equivalent to the contractibility of the single spaces, which is then equivalent to the contractibility of these simplicial sets. Yeah, so these are different sort of notions of weak equivalences. So here we have for all x, and we can detect these using homotopy groups. So we can look at pi n, no, not n, pi k e in x is 0 for all k n x. Oh, I should have written for all n. Sorry. So this can be rewritten as maps in the homotopy category of simplicial sets to here. So this is in simplicial sets, pointed simplicial sets, but by adjunction this is the same as this here in pointed spaces over S. And by another adjunction, this is the same as the shifted suspension spectrum of this thing. Using this description of the suspension here, relating it with the shift, this here becomes what we want. So this is an k minus 2n minus n suspension of x plus. And this proves the statement. Okay. So now I can say that at least there appeared one lemma with something like a proof in my lecture series. Okay, some notation for E, a motivic spectrum. One abbreviates usually this here as pi as W of E, and sometimes even like this. One wants to save more time, and this here might be abbreviated as this here, but this is maybe not such a good idea. I don't know whether I will use this. Okay. Yeah. As I already mentioned, these spectra KGL and HZ, they relate to algebraic K-theory and motivic homology. So these were sort of, in some sense, generalized homology theories on smooth varieties, which were now represented. When Wołodzki introduced the algebraic cobordism spectrum, MGL, there was no such corresponding theory, but now we have a theorem which is due to Levine, which over a field of characteristics 0 identifies MGL 2 star star with the Levine-Morel algebraic bordism. So this is this came up in Nikita's talks. And yeah, I should say, of course, there have been more computations regarding the coefficients, for example, computations due to Spitzweg and also to Jonas Killing for number for numberings. Yeah, but unlike the topological situation where we know the coefficients for the corresponding spectra completely, it's the complete computation is unclear here. Yeah, maybe I should also say this. So I had these complex, and realization functors, they extend to give a functor from the stable homotopy category of C to the classical stable homotopy category, and in the case of the real numbers, here you have the stable homotopy category of genuine C2 equivariant spectrum. Yeah. And if you like, you can try to identify the image of these three spectra under these realizations. Again, it's convenient to have geometric models. So in the case of algebraic K-theory, I basically discussed this. KGL gives you the periodic complex K-theory spectrum for MGL because of the way Thom spaces interact with complex realizations. We get the complex coordinate spectrum, and there's a way, the Suslin-Nowotzki theorem, to describe motivic cohomology via infinite symmetric products, and using this description you can then show that this is singular cohomology. And I invite you to compute the corresponding real pictures. Okay. Yeah, maybe in this context, let me mention the following theorem of Mark-Levin. Yeah, here we have, for complex numbers, a functor to the classical stable homotopy category. But for every base scheme, we have sort of the constant motivic spectrum functor, in particular for the complex numbers. And it's straightforward to check that this functor here has this constant functor as a section. So this here is, oh, yeah?
Realization of H isn't it finite coefficients?
No, it's true integrally.
Integrally?
Yes.
Ah.
Yes.
Okay.
I mean, we are in a situation, a field of characteristic zero, where we really have the infinite symmetric product as a suitable model.
Yeah.
I know that there are sort of singular varieties appearing when you construct this geometrically, but you can resolve these singularities, analyze the geometry, and get this property. I think this is written down carefully by Mark-Levin in a paper where he relates. Well, I think he proves this theorem. Yeah. There's another approach how to get this here. I'll mention that in a bit as well. Yeah. Okay. Constant. Yeah. So this here is a section of this functor. So we know it's sort of injective on objects and on morphisms, but what Mark-Levin proved is that this here is actually a full and faithful embedding. So motivic stable homotopy theory over the complex numbers is, in a very precise sense, at least as complicated as classical stable homotopy sequence. And the way he proved this theorem was to employ the slice filtration introduced by Mowatzki. And this is now sort of the passage to the second part of my lectures, which so far we've been in the part construction. Yeah, I've constructed or I explained the construction of this stable homotopy category, constructed some more or less interesting objects. Now comes the second part, which is computations. So there are sort of several computational tools available, and many of them are sort of motivated by similar approaches in topology. Yeah. For example, one can use the Motivec-Eilenberg-MacLane spectrum or its version for finite coefficients to set up a Motivec version of the Adams spectral sequence. One can use MGL or sort of the P typical parts, the Brown-Peterson spectra, to set up Motivec versions of the Adams-Novikov spectral sequence. What these give you are certain filtrations then, but I would like to introduce Mowatzki's slice filtration as a computational tool. And the definition is as follows. You look at the localizing subcategory. So it's generated by suspension spectra. There's no shift here. Suspension spectra of smooth varieties. And this is called the effective stable homotopy category. Yeah, and this here refers to the localizing subcategory. So in particular, it's a triangulated subcategory, and this inclusion here, let me call it I0, this is a triangulated functor, and using sort of this compact generation property, it's easy to get a right adjoint. This is one of Niemann's theorems. And this gives you sort of an endofunctor on the stable homotopy category, which sort of takes its effective part of any Motivec spectrum. And this can be now shifted around. So you have the 2nn suspension, where n is an integer of this effective homotopy category. So you can express this as the maybe I should. So that's generated by the 2nn suspensions of these guys. So the inclusion is then called In, and the retraction is Rn. And this gives us another endofunctor. This is called Fn. And it receives a natural map from the n plus first. And the cone is then the nth slice functor. And this can be thought of as a triangulated filtration on this motivic stable homotopy category, and it sort of measures the amount of GM suspensions you need to build a motivic spectrum. You can take as many simplicial suspensions and desuspensions as you like, but for the GM suspensions, there's sort of a lower bound. Yeah. So allowing these simplicial desuspensions gives us that this is a triangulated functor. Yeah? These are all triangulated functors, and this is very convenient for computations and sometimes very bad for computations. Yeah. So work by Pelaez, which was then sort of a bit improved by work of Gutierrez, myself, Markus Spitzweck, and Paul Arne Östwehr, gives that this is suitably monoidal. Yeah, this is probably nothing too surprising, but there's something one has to do. And in particular, we get the following formal property. If you have any motivic spectrum, then the nth slice is module over the zero slice of the unit. And this already tells us whether we actually have managed to find a simplification. So the idea is to get a filtration such that the associated graded, the slices, have a somewhat simpler structure. And for this reason, I mentioned the following theorem, which was proven by Voevodsky, first in characteristic 0, and by Mark Levine for a positive characteristic field. So if S is the spectrum in the field, then the zero slice of the unit is motivic homology. And of course, I can be, if you like, more precise in the following sense. So motivic homology is a ring spectrum. You have a unit map like this. Right, so by definition, this here is effective. It's in some sense the mother of all effective spectra. Or maybe it's not quite true. Let's see. So we get a map to the zero slice. And what characterizes the zero slice is that it's both effective and that there are no non-trivial maps from at least one-fold GM suspensions. And now, if you look at motivic homology over a field, it's one basic property that it vanishes in negative weight. This was mentioned by Matthias. So we sort of get a map here. What is not quite clear using the construction of motivic homology is that this is effective. But again, the Suslin-Voevodsky model using infinite symmetric products shows you that this is an effective spectrum and that this map is an equivalence. This works in characteristic 0. And the argument in positive characteristic is more complicated, and I would prefer not to mention it. I have 5 minutes left anyhow, there's no point. Okay, but I should mention in this context the following theorem. So if you have a field of characteristics 0, then the homotopy category of modules over the Einberg-MacLane spectrum is equivalent to Wodski's big derived category of motives. And this tells you that the associated gradient for the slice filtration, at least over a field of characteristics 0, are motives. And of course, this statement has been generalized. The vast generalization with rational coefficients is due to Brzezinski and de Vries. I definitely for S any base scheme, the homotopy category of modules over the rational Einberg-MacLane spectrum, which is then defined as a certain summand of the rational algebraic K-theory spectrum. This is equivalent to a derived category of motives over S with rational coefficients. So the slogan is that slices are motives and should be easier to compute. And let me give you one approach to computing slices. Which will also shed some light on this realization question, I guess. So we have this motivic spectrum MGL, and it has a universal property with respect to orientations, and therefore it receives a map from the Lazar ring. Yeah, so this is the polynomial ring on infinitely many generators. The degree of xi is 2ii. Yeah?
In this theorem, do you assume S is over a field or S is anything?
The person behind you can give you the precise condition.
So actually, we just need that S is a geometrical unibranch. But I think this could be bypassed now. And there's no base field.
No base field.
This is essentially because K-theory will be rational in that case. Without any base field.
Mm-hmm. Okay, so the condition that's in the literature is sort of geometrically unibranch. Yeah. Okay. Okay. So we have this ring map from the Lazar ring to the coefficients of algebraic Bordism. And this means we can take, we can consider these elements here as certain maps from spheres to MGL, and we can form suitable quotients in the category of MGL modules. And the following theorem is apparently due to Hopkins and Morel, but they never cared writing it down. But fortunately, Marc Rouillard did this and even generalized the statement. But the integral statement is valid over fields of characteristics 0. So MGL, by construction, is also an effective spectrum. Yeah, the spaces in there amount to Thom spaces of Grassmannians, and in the nth stage, it's the Thom space of a vector bundle of rank n, which tells you that in the nth stage, this is something corresponding to a 2n suspension. So in all, this is an effective spectrum. So it coincides with its effective cover, and you have a map to the quotient where you factor out all these elements coming from the Lazar ring, generating the Lazar ring. And the statement is that this here gives you the zero slice of MGL. And using the theory of orientations and sort of Landweber exact theories in the Motivik setup, which is due to Naumann, Spitzberg, Östwer, it is also straightforward to check that this here is then Motivik homology. Yeah, and if you use this description here of Motivik homology, and if you believe this property here, then you have to believe this property. Yeah. Okay, but let me stop here.
Any questions, comments?
By your complex realization, you mean your yesterday realization? Complex realization.
Yeah, yesterday's
Well,
realization was
simple things, right?
sort of a space level realization,
Yeah.
and yeah,
I mean,
but it's
the
extended in the
extension of your
obvious way.
realization.
Yeah,
I
yeah.
see.
So, in one of the theorems you said that if you take the GUS slice of the SPR spectrum, you get the Motivik homology
Yeah,
over a field.
over a field.
So, in what generalities is expected to be true if it's not a field?
So there's a recent, actually, there's this preprint by Hoyoa and Bachmann on normed Motivik spectra, and in, I think, the latest version, they give an argument saying that the zero slice of the sphere over the integers, or a Dedekind ring, is Spitzweg's Motivik homology spectrum, which is known to pull back over sort of maps to fields. Yeah? So, and conjecturally, this is true over any base.
Other questions? Okay, let's thank the speaker again.